And there are other mysteries of gravity which seem very hard to solve, which I'm just listing as like examples of questions that probably we're stuck on. Really key one I already mentioned is how can we reconcile general relativity with the standard model, which describes all the other forces. As I mentioned, general relativity ignores quantum mechanics. The standard model does not. They got to fit together. We probably need a theory of gravity that does take quantum mechanics into account. Another obvious one is what really happened at the Big Bang? Was there really a moment when everything became infinitely compressed? Or when you get really close to that moment, something else happens that we don't know what it is? Was there anything before the Big Bang? We don't know. What happens to stuff that falls into black holes? Does it just go in there and just disappear forever? Or does it like eventually, maybe the black hole evaporates and this stuff pops out in some form? We don't know. And what's the ultimate fate of the universe? That'd be good to know. Just get it over with here. So like watching a TV show, you only want to know what's going to happen. Well, we don't know what's going to happen. If by our best theory so far, the accelerating expansion of the universe will just pull everything further and further apart. So eventually every atom will be so far away from every other atom that there's like no form of communication between atoms anymore. And it'll become extremely boring. But we don't know that that's true. I mean, that's our best theory now, but it could be that like 50 years from now, we'll say, ha, 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 that's what they thought back then, those idiots. So we don't know. And another really great question is, why is the future so different than the past? As you've no doubt noticed, if you drop an egg, it goes, but there's no way to like unsplat it and have it pop back up into your hand, except by like making a movie of it, playing the movie backward. The laws of physics don't seem to completely prohibit that from happening. We tend to say, oh, that's extremely improbable because everything would have to be perfectly lined up to pop up into your hand like that. But that's a weak argument because in fact, everything had to be perfectly lined up at the beginning so that it would drop and splat. So there's some asymmetry between the future and the past that we don't fully understand. A lot of people trace it back to the Big Bang, but even then it's not explained, it's just being traced back to that. So all those are too hard. It seems easier to make progress on other problems. One other last big problem that I want to mention that we can make some progress on is this. Why don't galaxies or the early hot gas in the universe behave the way we would expect? Why do we seem to need some extra kind of matter, invisible, so we call it dark matter, or maybe a new theory of gravity? You see, there are a lot of funny things going on. Galaxies all rotate much faster than we would expect, given the amount of mass we see them having. The more mass is in something, the more it makes things, it attracts things gravitationally. So the more things around it spin around, and galaxies are all spinning around faster than we would expect. And in the early universe, galaxies form faster than we would expect, unless we say, oh, there's like extra mass there that in some form that we don't understand. Or maybe gravity doesn't work the way we thought. And thirdly, fluctuations, little ripples of density in the hot gas of the very early universe are more lumpy than we would expect, given the amount of mass that's around that tends to like collapse into lumps. So, yeah, so all of these are currently, people attempt to explain them by positing new forms of matter called dark matter that don't interact with matter in ways except from gravity, or at least not much, and that we don't really know what it is. It's not apparently not a particle in the standard model. The more rebellious alternative is to suggest that our theories of gravity are messed up and we need to adjust those. So there are also people trying to do that, fix our theories of gravity in a way to account for all this. So the good thing about this is that astrophysicists are learning a lot about this by doing lots of different kinds of observations. So it's a subject where we keep getting new clues. So this is sort of old by the contemporary rapid pace standards. This is called the bullet cluster. It's two large clusters of galaxies imaged in sort of some fake color here to indicate some things that are going on. And the idea is that these two clusters of galaxies crashed into each other and went through each other. And the visible matter, which is indicated by this bluish stuff, because galaxies are clusters of galaxies, their density is so low, it just plowed straight through and didn't really mind, it just went straight through. Whereas the dark matter, which is indicated by this pink stuff, did crash into itself and slow down, and that's why it hasn't gone far enough away. They've already gone through each other, now they're leaving. How the heck do you have a picture of dark matter? It looks like pink, not dark. It's because what we do is we measure how the light of galaxies behind this got bent by the force of gravity. So we estimate the amount of matter that should be there bending it. And there's this, and if there's no visible matter there, we say, oh, maybe that's dark matter. So this has often been trumpeted as like a definitive proof that dark matter is really there. But the people who believe in alternative theories of gravity actually have their own ways of trying to explain even this type of occurrence. So it's, I would say it's really definitive. Okay, so now it's time to summarize. So you've come to this talk about mysteries of fundamental physics, and you're going to walk off and you're going to read news stories occasionally, and you're going to wonder, like, okay, any progress yet on any of these mysteries? And so in this summary, I want to give you a little bit of advice for what to do in your future consuming of information about fundamental physics. This is assuming, of course, you're not a professional physicist, in which case you know perfectly well what you want to do. You don't need any advice, but I'll give it to you anyway. So don't hold your breath. It's the first key piece of advice. So progress has been very slow since 1980 compared to like from 1900 to 1980. And because of this slowness, and because newspapers have to keep selling newspapers, there's a lot of churn that winds up not mattering that much. So I would suggest that you don't pay too much attention to cool sounding theories that don't have experimental evidence. For example, there's been a whole huge discussion about something called the multiverse in the last 10 years. This is not the metaverse, which is like some other goofy thing. The multiverse is the idea that there are like many multiple realities. So basically, there's no way to obtain experimental evidence for that. And it's basically the kind of thing that physicists talk about when there isn't anything better to talk about. And this is a tougher piece of advice to give, but I also suggest not paying too much attention to surprising experimental results unless they've been confirmed. Of course, experimental results are what we really need, and that's how we're actually making progress now. So I'm not saying like ignore experimental results. It's that people are so hungry for new experimental results in physics that whenever there's some little deviation in some particle detector somewhere, if something is like 3 standard deviations away from what you expect, you will see articles in the science press saying like, oh, maybe the standard model has finally been proven wrong. And so far, although I see like about 5 such stories a year, so far for the last, say, I don't know, 5 or 10 years, they've all not panned out. So just wait until something is confirmed. Don't worry. If we really discover something, you'll hear about it. So I suggest, on the other hand, that it is good to stay tuned for news about these 3 things I mentioned: neutrino oscillations, dark energy, and dark matter. And the reason why is because these are mysteries where experiments and observations, astrophysical observations, keep turning up new clues. So this is like a fun story to keep following, where it's like a detective story where we keep finding new clues. And it's interesting that these 3 questions are related to what makes things have mass. Right? Neutrino oscillations are currently explained by the Higgs boson, which is the mysterious particle that makes everything have mass, or fundamental particles have mass. And what makes space-time bend? That is it Are there new forms of energy and matter which are curving space-time that we just don't know what they are? Or is our theory of gravity screwed up slightly? And that may be the explanation for what we're currently calling dark energy and dark matter. So these are things that we're going to slowly make progress on because we've got such great observational astronomers and experimental particle physicists working away on them. And so we're eventually going to have some new breakthrough, but I have no idea when it's going to be. So it's good to just like sit back, get out your popcorn, watch the movies and read physics books, because the amount of physics that we already know is amazing and it's so much fun to learn. You don't even really need new fundamental physics. Most of us don't really need new fundamental physics to keep entertained. There's a lot to learn here, and I've just skimmed over the surface of it. Okay, thanks very much.